Oh, okay, cool. Okay. Maybe I'll keep it closer to me then. Okay, guys, let's continue from where we left off last week. So I think we talked about acids, we talked about acid halides, and I asked you guys to do something for me, isn't that right?
Oh, yeah.
Was it for the anhydrides?
Acid anhydrides,
So
yeah.
let me summarize it, you guys can tell me. So, let's see, what is that? I think I drew out the whole thing and I asked you to fill in a bunch of things, am I right?
Mm-hmm.
Okay, so let me write out the base of basic stuff. So carboxylic acids can be used to make acid anhydrides, and so can acid halides be used, and of course carboxylic acids can be acid halides. I did say, I think that, okay, that does that, and we need either the carboxylic ion, or you can even use carboxylic, a different carboxylic acid as well. But then I do remember saying that in order to make anhydride from carboxylic acid, we probably need two of the same, because it works well for symmetrical anhydrides, not for unsymmetrical anhydrides. Did I say something like that?
Yeah.
Okay, cool. And actually, just a simple heating will be able to do an intermolecular dehydration. Basically, one water molecule is taken out to condense the two acids together. And as far as the reactions of acid anhydrides are concerned, we can convert acid anhydrides back into carboxylic acids, either use a dilute acid. Oh, were you going to tell me that, or did I?
Yeah.
Okay, okay. Or, what else could we use there?
Water.
Water, or,
The base.
so, say that again?
Base.
So an aqueous base, right?
H2O or HO minus.
Exactly. Okay, now can I convert acid anhydride into acid chloride? Is that doable? Can I convert an anhydride
No.
into acid chloride?
No.
No,
Why
because it's higher. The chloride is higher.
Exactly. You cannot go in the higher reactive direction, you can only go in the lower reactive direction. Okay, so acid anhydrides can be converted into esters, converted into amides, primary, secondary, or tertiary, depending on what you use. We can convert this into primary alcohols. We can convert them into aldehydes. We can convert them also into tertiary alcohols. Or we can convert them into a ketone. Are these the ones that I wrote out for us?
You didn't write them out, you were gonna have us.
You were gonna have
Oh,
us
shoot.
determine the products.
Okay,
They gave
oh,
us the
shoot, I wrote down the reagents, oh my
Yeah.
goodness.
I'm backwards.
Oh, I thought you were going to give me the reagents, okay, well, go ahead, give me the reagents first.
To turn a car.
Anhydride into a ester.
What would I use then?
An alcohol.
So once again, think of what is it's a substitution reaction, think of what is being replaced by what, and then decide what you should use. So what is the nucleophile in case of making an ester? What is being brought in?
An R group.
So, no, not R group actually, OR is going, this is the leaving group, this is your leaving group, this is the group that's been kicked out, and we write the mechanism a couple of times, but that's the leaving group, it's being replaced by R prime O, so how do I bring that in? Either use this, That's probably going to be the most effective, or you can use alkoxide. Isn't that right? The leaving group is, again, you have to think of what is a good leaving group. A good leaving group is a core base. That means the leaving group has to be not just this portion, but the entire portion, including that carboxylate ion, is the one that's being kicked out.
The OCOR.
So how do I convert it into an amine? Anybody? What do I use to convert acid anhydride into amine?
H and whatever.
Right? Exactly. All you need is one hydrogen here and then whatever. Next one. How do I convert the acid anhydride into a primary alcohol? Primary. So then? Exactly. You need a strong reducing agent, aka La with second step. Exactly. How do I convert it into an aldehyde?
The weaker,
The
La
weaker
H3.
Exactly, absolutely, which is the lithium trialkoxyhydride. Exactly, that's the weaker reducing. Good job. How about tertiary alcohol?
Wouldn't that be, Grignard?
Exactly, please also notice two of those R's are the same because reacts twice, just like, exactly like acid. So we need an excess, two or more equivalent of the Grignard, absolutely, exactly the same mechanism. How about next one? How do I convert it into a ketone though? No,
sorry.
Grignard will go tertiary alcohol. So, oh, did you say Gilman and I heard Grignard?
No, I was thinking that we were on Grignard.
But to get a ketone where only one R prime has been included, absolutely Gilman's, because that's the weaker organometallic reagent. Exactly. Please notice it's the same reaction, same outcomes. The leaving group changes, of course. Does that sound okay? Okay, let's try this out then. Okay. Please tell me the products. Let's start with, I'll number them, 1. Let's start with 1. What will be the product? Say again? Which one? Well, you know how to name now.
Oh,
Which one? Which specific one?
Butyric acid.
So which one? Did you say, what? Methyl, are you sure? Ethyl? Really? There's no such thing as methyl carboxylic acid or ethyl carboxylic. Let's use the names, guys. We know how to name them.
Butyric acid.
Countercarbons.
Propanoic.
Oh, propanoic acid.
It's a three carbon carboxylic acid. So yes, it's propanoic acid. Vincent, you're able to hear me, right? Just let me know if you're not able to hear me, okay? Well, yeah, so you gotta give me the name. Exactly. propanoic acid. Everybody okay?
Mhm.
Okay, how about two? Let's start, I'm just going in this direction. Two, what's the product? And we know the names, so please give me the names.
Sorry.
Okay, use the
How
ketone.
about propanol? We gotta go faster, guys, we're way behind. Gotta go faster, that's propanol. Okay, let's go to number three.
Oh, okay, propanol. Okay.
Next one.
Two, wait, what?
How about 1,1-diphenylpropanol?
That was what I was thinking. 1,1-diphenylpropanone.
Next one.
Propanol.
Four. Next one, guys, what's that?
Phenylpropanol. Phenylpropanol.
Benzylpropanone.
Although you won't call it benzylpropanol, that doesn't exist.
Okay.
I mean, if you wanna use common name, you can call it benzylpropyl ketone, but what's the IUPAC name? One phenyl what?
1-phenylbutanone.
2-butanol.
1-phenyl-2-butanone.
Benzylpro. Everybody okay?
Mhm.
1-phenyl-but-2 or butane-2-one. Okay, next one. We don't know, well, we do. What about that one?
Turns it into a primary amide.
Which one?
Propanamide.
Good, very good. Next one.
N-phenylpropanamide.
Good. And next one.
Mm.
I can write.
3-methyl. Mm-hmm. Good. Very good.
Would you have a PY with that?
So 3-methyl butyl, yes. Let me draw that.
Two,
1, 2, 3,
three.
4. So, yes, this is 3-methyl butyl.
So would that have a
Wouldn't
PY again?
Second,
What's PY? What's the name?
pyridine.
wouldn't it be
In this case, you don't need it because what's the leading group coming out is a carboxylic acid, and it's a weaker acid. If it were HCl being created as a byproduct, then of course pyridine might be necessary because HCl is a stronger acid. Everybody okay? Questions? Let's write the mechanisms. Notice again, everything is exactly the same as what we've seen before. So hopefully we can go through this faster. Let's start with number 1, which is hydrolysis of the anhydride. So what do you think? And please notice I used hydronium. So what should be the first step? Right? What's going to get protonated? There are 3 oxygens. Which oxygen will get protonated?
one of the C double bonded oxygens.
Do you all agree? Again, I could ask you why. Why do you think it's one of those oxygens that's protonated? Why isn't the central one protonated? Does anybody have an answer for me? Which is the correct curved arrow? The blue one, because that has lone pairs too, or the orange one? Why? Why is the blue one more correct or better than the orange one?
Because it's got resonance or not?
Who's got resonance?
The blue one has resonance.
Well, the whole thing has resonance. So what? So therefore what?
Can't you protonate the single bonded O to make it a good leaving group?
Okay, but that's what I'm asking. Is the blue one better or the orange one better?
The orange
And
one.
why?
the orange one because
Why?
it,
If you make the double bonded O's protonated, you also have a good leaving group, by the way.
okay.
Why? You started thinking resonance, but then you stopped short. Guys, when there are why questions, you can't just give a one-word answer. You gotta explain. You gotta explain it in such a way that the person who's reading it understands what you're trying to say. If you just say it has resonance, what does that mean? Explain. Please.
Stabilizer.
Who? Stabilizes what? What's the it you're talking about?
Carbocation.
Blew up the.
Really? The molecule is pretty stable as it is. Why do I need to protonate it?
Then let's just leave it alone.
So then we're not talking stability. Then we're not talking stability. So guys, here's something to consider. Your explanation tells a lot about how well you actually understand it. Because if you really understand it, then you can articulate it. When you don't understand it, then it's hard to speak it out. Absolutely, I do agree with you that the blue curved arrow is better than the orange curved arrow. I also agree with you the reason is resonance, but let's explain it. So, when I, let's say, draw out the resonance structure, a picture speaks 1,000 words. Let's draw out the resonance structure.
Oh.
Do you agree?
Yep,
What am I missing?
a negative charge
That's it? What else am I missing?
A positive charge.
and a positive
So
charge.
what's the hybrid? Do either of these structures exist?
No.
What does exist is the,
Hybrid.
what
Hybrid.
is the structure of the hybrid? Let's draw it out. Hey, here is the resonance structure and here is the hybrid. What am I missing?
The charges.
Partial charges.
Positive on the top, and partial negative on the bottom.
Does that answer your question as to which oxygen will get protonated? Well, the oxygen that has higher electron density should get the proton. And if you look at the hybrid, it is this oxygen or this, because the resonance could go in both directions. It's one of those oxygens that has higher electron density. So the proton should go to the oxygen that has higher electron density. Resonance is causing the double bonded oxygens to have delta negatives on them. So therefore, absolutely right, I 100% agree with you that the proton should go to one of those oxygens. So the first step, if you will, is either one of them gets protonated. Absolutely. So what does that structure look like?
H
Now
plus.
what? What would be next?
Double bond.
Water attacks where?
Electrophile of the.
Good, very good.
Electrophilic
Creates
carbon.
a tetrahedral intermediate. Okay, then what? It's the same mechanism.
Exchange,
over and over.
proton exchange.
Very good. Proton exchange. From where to where? This
Yeah.
is going to lose a proton,
And the
right?
bottom one will,
Who's gonna take a proton?
the bottom, OH, or
Okay,
what?
sure, we can do, yes, absolutely. So that can take a proton.
oh,
No, no,
that one?
That's okay, keep it that way. You're absolutely
That
right. Those oxygens have
Wasn't
higher
thinking.
electron density, so you're good.
Oh, okay.
Oh, did you mean, oh, sorry. I
So it could
misunderstood.
be either one, like
Which
the,
either one?
like the O?
No, not right now. Now there's a huge difference between them. That's OH, this is a double bonded O.
Yeah.
There's a difference between the two. Can I protonate this? Yes, of course I can protonate this, but then, does that take us in the forward direction though?
No,
No.
It just makes
but either
this
of,
OH and this OH too, same thing. Do you see that?
Yeah.
Sorry,
Mhm.
Mark, what were you saying?
so I guess you can protonate either of those two O's, but we'll see.
Well, which is more electron rich? Is the single bonded oxygen more electron rich or the double
Oh,
bonded
yeah, we go
oxygen
back to
more-
the first, yeah,
right?
yeah. yeah, got it.
Exactly.
Mhm.
So proton exchange, okay, so that gives us okay, what would you suggest we do next?
The same thing with it?
What?
Another
Nucleophile attacks again?
attack from water?
You won't need a nucleophile to think of where you're going. Aren't we supposed to kick out a leaving group now?
Yes.
Where's, how?
Then we need to make a living group, so
There is a
Pro-
leaving group.
there is a
already.
living group?
Yep, there is.
I don't see it.
Sorry, say that again? There's no O minus. You can't have O minus when there's acid. You can't have an anion in an acidic environment.
Mm-hmm.
Where's the leaving group? Here's the leaving group. Can this happen?
Yes, yes.
Can that happen?
Oh.
There is a leaving group right there. It's protonated, it's ready to go, it just needs to be kicked out. It's kicked out. What does that create?
An an oxy
It creates purple. Yes, creates purple surface.
creates a
And what does this
carboxylic acid.
protonated carboxylic acid need to do?
There's that proton.
Who's gonna take a proton? Probably water, because we're using hydronium. Water can come in, take that proton and give us carboxylic acid, of course. The point is, please don't make an anion if there's acidic environment, that's not possible. So everything, positive charges can exist in acid because it's a protonated environment, and there you go. Is everybody okay?
I'm a little confused. But
Got it? Sorry, what were you saying, Mark?
I got a little confused here. Let's see.
What happened?
So this one here,
Yes,
doesn't this
okay, let me
a
do it
double
step
bond?
by step. It's all resonance,
Mhm.
okay, and when I write it a little differently, you will recognize it absolutely. I probably wrote it in a weird way, but okay, let me write it again. Okay. How about, can this,
Yeah.
Yep.
and, oh, wait a second, hold on. Okay, I have to change this because we're doing acidic. If I'm not going to draw those arrows, then I have to do it differently. To make sure I'm not creating an anion, in an acidic environment. Can't have an anion. But then, okay. Let's start with that. Here's another way to show exactly the same thing. You've seen this before, right?
Yep.
Yes.
Have you seen that before?
See.
Okay.
Yep.
But then these electrons, I could put them here, but would that be a good thing to do when you're, what will this create if I were to? It would create an anion, with a positive, but this is not okay to do in an acid. Does that make sense? So I don't want to do that, because negative charges in an acidic environment, not a good thing. So how do I avoid putting a negative charge on that oxygen? Okay, what if these electrons just create a double bond there? But then can carbon have 5 bonds?
No.
So therefore, one of these bonds has to then go here and neutralize the positive charge. Does that make sense?
Yes.
Would that give us what we just showed? So this part will become,
Yes. Okay. I see it. I see it.
Yeah, absolutely.
this part would become, right?
Yes.
Okay.
And then of course that has to be.
So we're not breaking the bond between the top hydrogen and oxygen, right?
You ultimately are, in this step, you are, because you need to get rid of that proton.
Oh, in that step, yeah, but in the first step you're not, right? Because initially, you know.
Another way to show. Initially, oh yeah, initially I had a curved arrow going from there. I see, then I can't have it. Either is fine, you can show it either way. Either way is fine. But are you all following the patterns though?
Mhm.
Protonated, whichever oxygen has the highest electron density got protonated, then nucleophile attacks, kicks out the leaving group. Again, you got to adjust the protonation depending on what is it that you're trying to kick out. Sounds okay?
Mm-hmm.
Let's write the mechanism for reaction number 2, which is the law reduction. Please you tell me, how would that go? The law reduction, so what do we have? Okay. Step number 1,
Nucleophilic hydride attacks one of the electrophilic carbons.
because there's no acid, right? So there's no protonation, which means the nucleophilic hydride attacks one of the electrophilic C double bond O carbons, okay? Whichever one, and that creates your tetrahedral intermediate. Okay, next step. Anybody? Oops, sorry, I made a mistake.
It's not OH.
Yeah, right, exactly, you're right, absolutely. Yes, next step.
The O, the electrons from that oxygen go back and form the double bond
And kick out. the
and
leaving
kick out
group.
a leaving group.
So the leaving group gets kicked out, that's your leaving group, creates an aldehyde. Agreed?
Mhm.
Next step. What happens to the aldehyde?
It
was
gets,
on the
it
quiz.
goes law attacks again.
Exactly. The law attacks again because the aldehyde is very reactive if there's law present, of course. So yes, exactly, it reacts again. But can it kick out anything this time? Is there a leaving group this time?
No.
There is no leaving group this time, so it stops right there. Am I right?
Mm-hmm.
Yep.
What is next?
Protonate.
Exactly. Where is that coming from?
Long.
So law reacts twice because the first step, the leaving group is being kicked out, then it reacts again. Make sense, everybody?
Mm-hmm.
Okay, reaction number 3, which is the Grignard reaction. It's exactly like the law reaction. Isn't that right?
Yep.
Can I just take a shortcut here? Grignard reaction is exactly like law because instead of H minus, it's R minus reacting. So you end up with an R here, which means it reacts again. R MgX reacts again in exactly the same way, which means we end up with 2 R's, which gives us an alcohol. Exactly the same mechanism the 2 reactions have. Agreed?
Mm-hmm.
Okay, let's go to 4. What is 4? Oh, we're not going to write mechanism for that. How about choose one, 5 or 6?
Six.
Okay, let's do
Okay,
6 then.
6.
That's with aniline, okay. Making a amine. So let's look at 6 then. Step number 1, please suggest.
Nucleophilic nitrogen attacks one of the C double bond O's.
Good, because there's no acid, there's no protonation, so nucleophile attacks, creates a tetrahedral intermediate. What's next? Oh, sorry, hold on. And next step, guys.
A gas exchange or proton exchange.
Where, from where to where?
From the nitrogen, sorry, the oxygen takes or accepts the proton. that
Which
comes
oxygen?
with
The single bonded O.
Negative, right?
Yeah, the negative
Instead
O.
of, because this is in a non-acidic conditions, I wouldn't do that. I would keep it simple, kick out the leaving group, because remember we have to kick out the leaving group. Just kick out the leaving group, which creates what? Which creates a carboxylate ion. Can the carboxylate ion take a proton?
It's in a basic
Well,
environment.
but, so can it take a proton? If it's in a base environment, can a base take a proton?
Yes.
Or who else could take a proton? Instead of the carboxylate, is there something else that could take the proton?
Another instance of the H2N.
Exactly. Instead of this taking a proton, another equivalent of the, probably a stronger base than the carboxylate, which is the original amine, those are basic, could take the proton. That's totally fine. You can show either taking the proton. Because the reality is, in reality, the carboxylic acid will not survive, because as soon as the carboxylic acid is created, another equivalent of the amine will actually come and take this proton to create the carboxylate ion plus the ammonium salt. So in reality, that's probably what you would get anyways. So who you show as taking the proton is actually not that important, as long as you understand that one of these has to come and take that proton. Whichever. Is that okay? Okay, let's do the esterification reaction mechanism. So once again, what do you think the first step would be? Are we all getting bored with writing this over and over again? Little bit. So would you want to do it at home?
No.
I love the sound. Okay. So first step. Can I just say ROH?
Yeah.
The R is that whole big thing. Okay, what's going to be the first step? Was there an acid in the reaction? No.
It was an alcohol,
There is
so
no acid, so no protonation. Okay?
Just slam the oxygen.
Okay, fine. Same thing, exactly. I want you to recognize that the mechanisms are exactly the same. There is really no difference going from one reaction to the other, because what's really happening is the same thing over and over and over again. That gives us this plus and then carboxylate can come and take a proton, give us the product. Sounds okay? No difference in the mechanisms. Questions? Okay, let's talk about esters then. So this was acid anhydride, also very reactive. Let's talk about esters. Now esters are again biochemically very relevant family of compounds. So aren't we doing a lab tomorrow where we are making an ester?
methyl salicylate.
Salicylate lab. That's an ester, methyl salicylate. It's an ester between methanol and salicylic acid. Okay, so let's talk about this. Esters are compounds that are considered to be a combination of carboxylic acid portion and an alcohol portion. So the OR actually comes from the alcohol, and the brown part is the portion coming from carboxylic acid. How do we make them? Well, there are different ways of making them. One is to react a carboxylic acid. What would you react it with? Can someone tell me? Louder? Which is called what?
An
An
alcohol.
alcohol. You guys, let me make it a prime so it doesn't have, the R's don't have to be the same. But this is done in presence of an acid catalyst. Not just the alcohol, we need to have a H plus as a catalyst. This reaction is, if you ask a biochemist to make an ester, this is what they would do. This reaction is called Fischer's esterification. I think that's what we are doing in lab, is a Fischer's esterification. Can someone tell me what's the byproduct? If we do Fisher's esterification, convert a carboxylic acid into an ester, what is created as a byproduct?
The H.
If I wrote it a little differently, I'm sure everybody will be able to tell me the answer. So let me write it a little bit differently. It doesn't really change anything, except that you need to start focusing on the details there.
Be water, right?
Exactly.
Yeah.
Here is your carboxylic acid portion. Here is your alcohol portion. What is not part of the ester?
Water.
Water. Water. So, the reason I'm bringing that up is, if I wanted the Fisher's esterification to go in the direction of the ester, this acid has to be a concentrated acid. Concentrated meaning what?
There's more acid than water.
Exactly, less water because of the Chandler's principle. But if there were more water, what do you think would happen?
The reaction would favor the carboxylic acid.
Exactly. This can easily be hydrolyzed back into the acid by using a dilute acid. Lots of water, therefore the Chandler's principle kicks the equilibrium back to the carboxylic acid. And that is the reason why organic chemists like us, I don't like that reaction, because there's this whole equilibrium thing that you have to play with and factor in and all of that stuff. What if I were going to make an ester, instead of carboxylic acid, I would just use acid chloride. A very fast reaction, very clean reaction, from an organic chemist point of view obviously, very clean reaction. Don't have to worry about back and forth. And how do I get an acid chloride? Well, I get that from carboxylic acid by using it, reacting it with vinyl chloride. Or we could also convert an anhydride, as we just saw, into an ester by reacting with the primary alcohol as well. Where does the anhydride come from? Well, the anhydride comes from acid chloride, or it could come from the carboxylic acid, as we've already seen. Everybody okay?
Mm-hmm.
Cool. Reactions of esters. Again, I hope you're seeing the patterns here, because nothing is new. Everything is exactly the same. Let me color code it so that esters can be hydrolyzed back into carboxylic acids by using a dilute acid. Or, have you guys heard of this word, saponification? Has it come up in biology at all? Sorry, say that again? Yes, I was actually going to write it. This method of hydrolyzing an ester back to carboxylic acid is called saponification. Has that come up in bio?
No, haven't seen it.
Has anybody made soap at home?
No, we haven't.
Does anybody know how to make soap? The word comes from soap making. The word saponification comes from the soap making process. Does anybody know how soap is made? You take fats, fatty oils, whatever kind, different kinds of fats, depending on what kind of soap you want to make. What is fat? What are fats? Esters. Fats are esters. Fats are really an ester between different kinds of alcohols and triglycerides. You may have heard of the term triglycerides.
Yep.
Right? What are those? So fats are esters, basically, if you look at it. And when you're making soap, what we are doing is we are hydrolyzing the ester portion to create alcohols and carboxylate ions, and that is the process used. Have you heard of the word lye?
Yes.
What is lye?
NaOH.
That's sodium hydroxide, highly concentrated, it can hurt. So you gotta be careful because it's very, very concentrated. But we are basically using lye sodium hydroxide, although in lab we don't use that high concentrations. And hydrolyzing the ester into carboxylic acid and alcohol. So because this method is used in soap making process, the term saponification comes in.
Wait, so are we making soap now?
No, we're not. We're making the ester soap. We'll have fun the last lab day of the quarter. That's when we make nylon and do tie and dye stuff.
Well, I had a question. For that
Yes.
one, are we only tie-dyeing with indigo or are we?
Yes,
making-
unfortunately, because we don't have dyes to put in there that would appropriately hold the color. So, but that, you can be really creative even with the last quarter we had really creative designs. So, I'm not creative, so I'm gonna let you guys do that. Okay, next reaction of esters. Esters can be converted into other esters, which means the alcohol portion can be switched. This is called trans-esterification, meaning one ester is being converted into another ester. So what are we using? Well, exactly like Fischer's esterification, we're using an alcohol with an acid catalyst. So it is Fischer's esterification. Instead, we are converting one ester into another ester. The mechanism is exactly the same, which we will write, but just FYI. We can convert the esters into amines using amines or ammonia, depending on what kind of amine we want. We can convert esters into primary alcohols. Can someone tell me what to use? Exactly.
Law.
Nothing is changing here. We can convert the esters into aldehydes. What are we using for that? Something similar to the trialkoxy aluminum hydride, but slightly different. It's called DIVA. I'll tell you what that stands for in a second. DIVA is kinda sorta like the trialkoxy lithium aluminum hydride. So DIVA stands for di-isobutyl aluminum hydride. So DIVA. Structure, basically it's aluminum hydride attached to two isobutyl groups. 1, 2, 3, that's one, and here's the second. So again, it is a weaker reducing agent than La, but definitely stronger than sodium polyhydride. So that stops at the aldehyde, doesn't go further than that. Can I react esters with Grignards?
Why not?
Why not? Okay, I like that. What will the outcome be?
Why not?
Anybody? What would the outcome be?
A tertiary alcohol?
Is that a question, Carter, or answer?
Tertiary alcohol.
What about the rest of you? Do you agree with Carter or you're thinking?
Who's got that O there? So.
We've done this before, we've written the mechanism last quarter, and you're absolutely right, tertiary alcohol with two of the same R's. Guys, the mechanisms are the same as what we are seeing, so you hopefully can work through those in your minds to figure out what the product should be.
Is that the same as like acid halide?
Yes, exactly, yes, exactly the same mechanism, yes. And can I convert esters into ketones? Using what? hopefully everybody is way ahead of me because it's exactly the same reactions over and over and over again. Do you guys agree? Everybody is okay with that? Okay, let's write a few mechanisms here. Some of these mechanisms are actually very important. So let's write a few mechanisms here, and again, because we've written them before, hopefully you can guide me as to how they go. So what if we have benzoic acid reacting with isopropanol lactosic acid. What would the outcome be? Anybody? I'm hoping for faster responses. I'm hoping for people to speak up more, guys. Because it's totally okay for me to talk for 2 hours, go back to my office, but I believe that at community college we have the luxury of actually interacting with each other. So I'm hoping for faster responses. What would the product be? Absolutely, isopropyl benzoate, exactly.
Isopropyl
The acid
benzoate.
portion is combining with the alcohol portion, giving us an ester. Absolutely, isopropyl benzoate. Let's write a mechanism. First step, please tell me.
Nucleophile tax electrophilic.
No. There's an acid here. Notice tosic acid right
Oh, so it
there.
doesn't.
First step.
So the so the double bonded O gets
Very
protonated.
good. The double bonded O gets protonated because that's the more electron rich oxygen because of the resonance hybrid. Then what? And the nucleophile is the alcohol.
The isopropanol.
Where does it attack? It attacks at the electrophilic carbon. Double bonded carbon creates your tetrahedral intermediate. Next step.
Okay, so
Protonate, no,
Protonate what?
another one of the alcohols,
Okay, and
making a these.
so can we just shorten that and say a proton exchange? Because I don't think you've seen that there. This one has to lose a proton, right?
yeah,
And one of the others has to take a proton. So proton exchange, absolutely, which you're right, creates a good leaving group. Absolutely. So next step.
Get a lone pair from the other oxygen, move it down, and then kick out the water.
Kick out the leaving group. Now, again, you guys were asking me earlier, do you kick out the leaving group, make a carbocation, or do you do this? I mean, in my opinion, either is okay because those are resonance structures of each other. And resonance structures don't really exist. What exists is the hybrid anyways. Does that make sense what I'm saying?
Totally.
Right?
Yep.
So whether you do it through the carbocation, which is a resonance structure, or you just do it directly, that's like a personal preference thing, neither is it. So what does this need to do now?
get rid of a proton.
And who's gonna take a proton? Again, an alcohol can take a proton, tosylate can take a proton, although tosylate is a weaker base. Something has to come in and take a proton and give us. This is Fischer's esterification. Guys, this mechanism is a biochemical process called Fischer's esterification. Is everybody okay? Or water, is water also making? Is everybody okay?
So it doesn't matter who takes the H?
Say again?
It doesn't matter if TSOH or
So
which
there
one?
are multiple candidates here who can take the proton. There is another alcohol can come in and take a proton, right?
Mm-hmm.
Mm-hmm.
Or water, we created water right here, didn't we kick out water?
Mm-hmm.
Yes.
So water could come and take a proton, or TSO minus can take a proton. But out of these three, which is the weakest base?
TSO.
Tosyl
This is
oxide.
the weakest.
Tosylate.
Exactly. So if you showed that taking a proton, I'm like, okay, fine, whatever, big deal. But more likely, it's either the alcohol or water taking the proton. Isn't that right? Because their basicities are about the same as each other.
Could it be just a proton floating around?
You can show that too, totally fine. Like what I did, right? Just
Okay.
deprotonated, you're gone. That's fine too.
Okay.
As long as you're keeping track of those. Everybody okay? Questions? So this is a mechanism called Fischer's esterification reaction. This is an important mechanism to make sure you know how to do. Okay, let's write a few reactions and we talk about the mechanisms later. Let me draw it out, please. Give me a second. I have more, but I have to scroll down. I don't like to do Zoom things. I can't write as much. Okay, let's do these first and I'll write the rest later. Can someone tell me what's the product from the first one?
2-methyl propanol.
Very cool. 2-methyl propanol. Plus, of course, this portion also gets kicked out, right? So what will it become? It also becomes its own alcohol, although we don't really care about it in case we are really interested in that portion. But just for us to recognize, the leaving group is also being kicked out. Okay, what about the next one?
Diba converts it to an aldehyde.
Which one?
2-methyl propanoic acid.
Acid or
2-methyl propanal.
2-methyl propanal.
Mhm.
Plus, of course, that portion, the other portion becomes the alcohol, which is okay, next one.
H3O.
The first two do the same thing.
First two will do the same thing, yes. So what would it be?
Cyclohexane carboxylic acid.
Cyclohexane carboxylic acid, and what happens to the alcohol portion? That becomes the alcohol. It's kicked out. What about the last one?
The esters would just swap, right?
So that's transesterification. Did I do that right? Now, of these reactions, guys, you should be able to write all the mechanisms. Well, not DIVA is okay if you don't, but we should be able to write this mechanism, this one, and transistor, because it's the same. Everybody okay? Please practice writing all of these mechanisms. Make sure you know what is the sequence of events and so on and so forth. Is there any one of the mechanisms that you would want us to write here together, or you guys got it?
I think we can write the NaOH H3O plus the
Okay, so you
the
meaning like
saponification.
Got it. Please tell me what would be the first step. Anybody?
OH,
Yeah, the OH would attack the.
You mean OH minus?
yep, OH minus would,
Hydroxide, because there's no acid in step number 1, so nucleophile attacks. What is that going to create? That creates
tetrahedral intermediate.
good. What will happen next?
Acid,
There's no acid yet.
no acid just yet.
The other charge will come back down and kick out the.
So kick out the leaving group.
Mm.
The tetrahedral intermediate will kick out the leaving group. Okay, next.
Acid comes in.
Okay, so good. I'm glad you asked us to write this mechanism together, because please guys think about it and then tell me. Will this survive?
No,
Will these two things survive being together?
No.
Why not?
because ethoxide could take back the proton.
We have seen many reactions where ethoxide is a base. So if there's a base, there's an acid, they cannot survive. The base will take the proton from the acid. There is no way you can stop that. So at the end of step number 1, this is where it stops. Everybody okay?
Yeah.
We get the carboxylate. We don't get carboxylic acid. That is the reason we now need to add so that carboxylate can be protonated. And that's very important to recognize. If you instead write it this way, do you think instead of going in that direction, if you just went from here, let's just add acid and have this guy come take a proton, that's wrong. No. Because before we can add the acid, the base has already taken the proton from the carboxylic acid. So there is no way that these two things can coexist together, because they will react and become this. That's where it stops. Is everybody seeing that, following that, understanding that? Okay, cool. Let's write more. Please tell me the products.
The Grignards is would result in a tertiary alcohol.
Okay, which one?
One, two, three. Let me draw the structure. One, two. 1, 2, 3, 4. 1, 2, 3, 4, 5.
Is it 3-ethyl, 2-methyl,
Free ethyl, 4-methyl.
4-methyl? No.
Oh, free ethyl 2-methyl pentanol.
Is that what everybody's getting? Okay, make sure you know how to write the mechanism. Next one. Ready?
2-methyl free pentanone.
Pentane 3-on.
2-ethyl pentane
Next
freon.
one. Yes. Next one. I don't think you can name it.
I don't think we can name the
We have a
cyclic
okay.
cyclic
Do you
amide.
agree?
Yep.
Okay. This mechanism also everybody should be able to write. Again, it's the same mechanism over and over again. There are a couple mechanisms that I think we all need to work on together. So here is the first one. Is everybody okay with the reactions though? Does anybody have any questions? Please go ahead. Tell me what the product would be. No, you can't name it. That's okay. We have not learned how to name that, so you don't have to worry about name. So,
So you just want the answer?
the product for now. And then these mechanisms we will write together. Products first, then we'll work on the mechanisms.
So you want to tell it to you without telling you the name?
Say again?
You want to tell it to you without telling you the name?
That's, yeah, oh, you can go right there too. It's hard to, you can go right on your screen. The names we won't be able to, because, I don't know if you've, oh, I guess we could have, that's okay. Just
Oh,
wait.
this is how you write. I thought you like always did on like a mouse keyboard.
No, no, that's too hard, yeah. That would be too cumbersome. Yeah. Cool.
Awesome.
What do you say?
I got it right. I was
Perfect.
wondering.
No, no, you're absolutely right. That's an ester.
I was wondering if they were two separate or one.
No, well, are we
But I saw,
breaking this
yeah,
bond?
no.
You're
No,
cleaving
We're
you're
only breaking that bond.
Yeah.
you're cleaving the CO single bond.
And, yeah, no, that's how I did it, but I was.
Absolutely, you're absolutely right.
Never been more jealous.
Very cool. Yep.
So I assume you wouldn't have water as a byproduct for
Hey,
the
go.
last one?
Say it.
You wouldn't have water as a byproduct for the last one? Because you only the oxygen.
Yeah,
moves
no,
out.
exactly, you're right,
I might be wrong.
yeah. Proton is used, proton is created, but no, yeah.
So then your base would have to be the ETO instead of water.
Yeah, let's write mechanisms and answer that question too.
Go, Margo.
Whoa.
There's a, yeah, that's okay, do that, otherwise there's a button there for it. But that's okay, Mark. Oh, that too. Yeah, yeah, it's fine.
That's an H.
Yeah, that's an H, yeah.
Everybody controls.
Maybe you guys agree that it's not fun to ride on that thingy. Yep, exactly, that's cool, yay.
I need practice.
Let's write no, that's really great, guys, let's write mechanisms quickly for these 4 reactions. Am I able to annotate, Vincent, you're there too, right? So maybe, if I were to annotate, no, I can't do that, okay, fine, okay. Let's start with the first one, so what's going to be the mechanism for the first one, guys? Step number 1?
Bring your text, the carbon.
Exactly. Please notice, nothing is changing, nothing is changing in terms of the steps. Grignard attacks, creates a tetrahedral intermediate. What happens next?
The negative charge goes back, the electrons and negative charge go back and
And
kick out the leaving group.
kicks out the leaving group, exactly. When the leaving group gets kicked out, it creates a ketone in this, right?
Mm-hmm.
2, 3, O minus. Next step.
And then,
Bring
bring your
modes back.
text again.
Ketone can't survive. If there's Grignard around, the ketone's gonna react very quickly with the Grignard again. So it reacts again. And this, this is where step
Step
number 1 ends.
Stops.
Because now there are no leaving groups for that to kick out and no other place that the Grignard could attack. Isn't that right? So
Mm-hmm.
this is where the first step stops. So therefore, next step, when you add hydronium dilute acid, of course, you're adding lots of it. So both the minuses are the remainder. Sounds okay? Everybody okay with that? Yeah.
So if the Grignard isn't shown in excess, doesn't it just deal with the CU allowed?
No, so see, that's where that's where the whole process becomes extremely bad. So let me tell you what I mean. Let's just take hypothetical example. Let's say I have 100 molecules of this. Let's say. And I take 100 of this. So some molecules of the ester react once. Some molecules of the ester react twice, because it's all together, right? You got all of them together in one pot and you're stirring it. And then therefore some of these will have no more Grignard left to react with. So you'll end up with what we call a dirty product mixture. Some molecules were able to go through the whole thing, give us the final product. Some molecules don't have enough, so unfortunately they're like, okay, what do? We stop right here. And that means some of them don't have enough to do anything. That's not a process we want to do. We want reactions that are clean, that are taking us exactly in one particular path and not creating any complexities into that. So the point I'm trying to make is, if I were reacting an ester with Grignard, I should not have less than 2. So it's not an efficient way.
More.
Absolutely.
And
It's
then-
so much easier to have excess because it's actually easier to remove extra Grignard from the reaction, as you may have noticed in ours, than to remove extra that.
So, but when you react with the CULI, with the RCULI in lab, then it will stop
No,
right there,
that
and then they
stops.
get protein.
Because our Gilman's reagent is not strong enough to react with this. The ketones, aldehydes can't react with Grignard, so that's why it stops. Okay. Grignard is a strong organometallic reagent. Gilman reagent is slightly weaker, so it doesn't go. Does that make sense? Camilla?
Yes.
Okay, let's look at the next one. What is the next one? Hydrolysis.
Mm-hmm.
You guys can write the mechanisms because we've seen them already. Yeah?
Yeah.
Okay, cool. I'll let you guys do this then. Let's talk about the last family of organometallic reagents, and those are amides. Amides are the least reactive of all. These, if I want to have amides do a certain reaction, I would have to push it. And what do you mean by pushing it? Well, probably refluxing for a longer period of time, heating for a longer period of time for them to do something, because they are not very reactive compounds. Amides can be, have we already looked at primary amides, secondary amides, and tertiary amides?
Yes.
Okay, so you guys know what's the difference between primary, secondary, and tertiary amides. How do we make amides? Well, again, just if you're noticing the patterns, we can convert either carboxylic acids into amides, or we can convert acid halides into amides, or anhydrides into amides, or esters into amides. Because these are all more reactive than amides themselves. As we've also seen, carboxylic acids convert into all of them. And we've looked at that already. We've also seen how the more reactive ones can be converted into the less reactive ones. We've seen all of those paths. And I'll let you guys fill in the details because we've already done that. Everybody okay?
Mm-hmm.
Now what about the reactions of amides themselves? All carboxylic acid derivatives can be converted back to the parent carboxylic acid by one of two different ways. One is acidic hydrolysis, the other is basic hydrolysis.
Basic hydrolysis.
Saponification is actually only for esters. For some reason that term, because soaps are made out of esters. They're not made out of other families, right? So the term saponification is used only for esters.
Aromatic oils are also from,
Say that again?
aromatic oils are also from esters made of esters.
Aromatic oils. Aromatic means anything that has aromaticity.
Mhm.
Oils are fatty acids. Oils are fatty acids, oils, they have very similar structures.
So they're
Is
from
that what you're
esters.
talking about?
Yeah.
That does, yeah, so it doesn't matter which esters, the point is saponification is used when esters are hydrolyzed to carboxylic acid, under basic conditions. So I would not call this saponification because it's an amide, not an ester, but yeah.
No.
But as we said, amides are very unreactive. So if I wanted to do that, I would have to heat. I would really have to cook it, heat it, otherwise it's hard for them to do it. They don't want to do a whole lot of stuff. Can react with La, but now here's a difference, please note. Yes, they do react with La, but like other families where La would create a primary alcohol, this actually creates an amine.
A primary.
Not primary, because that depends on what's on the nitrogen,
Okay.
but the C double bond O becomes a CH2. So it becomes an amine. Primary, secondary, or tertiary would depend on what's on the nitrogen atom. But C double bond O of the amide gets reduced to CH2. Becomes an amine. Another reaction is, and this is only for primary amines only, for primary, for primary amines, I'm sorry. Only. I can dehydrate, meaning remove water, and that converts it into a nitrile. Removes water, makes a nitrile, but that's only for primary amines can do that. And that's it. We don't need to know too much more about amines. By the way, please keep in mind, have you guys talked about peptides in your biology classes yet?
Yes.
What are peptides? What are amino acids?
NCC, NCC.
NCC. What does that mean? NCC. What does that mean?
Carbon,
You're right.
carbon,
N
nitrogen.
is the nitrogen N, C is the carbon N. I get that. Of what?
The nitrogen is an amine.
Okay, of what? What is the parent molecule?
The,
An amino acid.
The amino acid.
What is an amino acid? All amino acids are basically, they are alpha amino carboxylic acids, which means they have, in the neutral form, obviously the biological pHs, have you guys heard of the Zwitter ionic form? Have you talked about that yet?
Zwitter ions are.
Yes or no? Yes?
Yeah.
Okay, cool. So, but I'm looking at the neutral form, pH and all. So, the point is you have an amine and you have a carboxylic acid. So, what is a peptide? What's a peptide?
A peptide is two of these amino acids linked together.
Or more, I mean, it depends
Yeah.
on what's the size of the peptide. But yeah, the point is that it's an amide bond. A peptide is not, oops, sorry, wrong. What are you doing, Sunita? What are you doing right there? Sorry. Erase. There you go. Peptide is nothing but an amide bond. There we go. When two amino acids combine with each other, one uses its C end, the other uses its N end, and creates, that's nothing but an amide.
Mm-hmm.
And then what happens, what's the bigger form of peptides?
Proteins.
Proteins, exactly, you're absolutely right. Proteins, as the chain gets bigger and bigger and bigger and bigger, that gives us proteins. Cool. Anyways, coming back, that's kind of sort of all we need to know about amides, that's really what they do, they don't do much. So let's try just a couple of examples and you can tell me what the product would be.
They're not reactive phase.
So no, nothing much, no, yeah, that's it, exactly, nothing. You guys tell me what's the outcome of these processes? What's the first one?
Second, the first one, the product is a nitrile.
Which one?
SOCl2, benzamide,
Is this what you're thinking, Carter? Benzonitrile?
Yeah, oh yes, benzonitrile.
Okay, next one.
Does it have to be ROH
Okay.
for the first step? For the first step, doesn't the reagent have to be, what reagent have to? Yeah, yeah.
For the first step, you mean for the first reaction, first step? What's the outcome of step number 1? Do you mean this one? Is
No,
that what you
doesn't
think?
the reactant have to have a alcohol?
No. This is a different reaction. What you're thinking about is alcohol being oxidized to carboxylic acid. There's no alcohol here. What happens to the side chain? Anybody wants to remind us as to what?
Na2Cr2O7 and
So what does that give us? Exactly. So what will that give us in this case?
benzoic
This
acid.
whole R gets oxidized, except for T-butyl. You remember that?
Yes.
And then of course everything else happens. Okay, product for next one?
The product is a carboxylic acid.
Okay, and no, I don't, well, you can name this, yeah, you can name this. Which one?
Propanoic acid?
So where's the nitrogen
The
then? You're breaking this bond, right?
yeah, you're cleaving.
And of course, the OH minus is going here, right? I'm
Yeah.
not writing a mechanism, I'm just processing it. So what happens to the nitrogen then?
It still stays on the molecule.
On which position? 1, 2, 3, 1, 2, 3.
1, 2,
And
3.
there's a methyl on it as well.
Yeah. So you're just breaking open a ring.
If I asked you to name this guy, could you tell me what the name of this carboxylic acid is?
Is it N-methyl butadiene?
Ooh, where's the amine part?
No.
Butaminoic acid.
Amino, butano, no? What's the parent?
Bu-
The parent is propanoic acid.
1, 2,
no?
3.
It's not a butanoic acid because our fourth carbon is not the chain. There's a
Okay.
nitrogen in the middle.
Okay.
So it is 3N-methylamino propanoic acid.
Free N-methylamino propanoic acid.
Agreed? Everybody? Okay, cool. So that's kind of the end of this chapter, whatever the chapter number is, 21.
20 and
Basically,
21.
all the acid derivatives, the reactions. It's mechanism heavy, but it's the same mechanism over and over and over again. So let's stop here. The next 2 chapters are, I'm going to look at chapters 22 and 23 as one, because there's a lot of similarity in them. So I know the book has separated them into 2 separate chapters, but I'm going to actually cover them as one big chapter. 22, 23 will be together. This chapter has a lot of mechanisms, different mechanisms, and a lot of ways in which aldehydes, ketones, and esters are going to come back, and different reactions that they undergo. Very, very important reactions in these 2 chapters. So we'll start that on Wednesday, and after that, I think I can finish these 2. I hope I'm not jinxing it. Maybe in 3 to 4 classes. And then probably 1 more class after that for chapter 24. So that is what, 4 to 5 more classes? I think I can do that. Which leaves, how many classes does that leave? This is week 6, so.
Week 6 of 4.
Oh, then we have a Monday off, don't we, for Memorial Day? Does anybody have a calendar? How many more weeks after? This is week 6, so 7, 8, 9. That's 6, but minus 1, 5, and then this one's 6.
5.
So I think we might be able to have at least 2 classes with no new content, which is the time when I want us to practice on old ACS exams. That's why I want to finish as quickly as possible. Well, not too quickly, obviously, but at least leave 2 classes where we practice old ACS exams so we get a feel for those exams. That's my plan. Sounds okay, everybody? Cool? Okay. Let's do next 2 chapters starting tomorrow. Have a wonderful day, everyone. Lab tomorrow, right? How many labs left?
This is the last actual one, I think.
No, aren't we doing aldehyde enigma?
Yeah, we're doing aldehyde enigma, and then the
That we're doing the
So that's a 2-class lab. So total of 4 labs. You're right. 2 of them are fun. But then methyl salicylate, which we'll finish tomorrow, and then the aldehyde enigma that goes over 2 classes. Okay, cool. Got it. Isn't that right? Am I thinking wrong?
I think I saw something wrong. I don't know.
You can go. It's okay. We're done. Bye. Thank you. See you tomorrow. Yeah.
How long is that?
Ochem.
How long?
I don't remember the procedure actually, to be honest. I haven't read it. I think there's an hour-long reflux, and I think there's a little extraction.